In this video, I want to talk about the three forms of the way in which we state the zero conditional mean of errors assumption, which is one of the Gauss-Markov assumptions. So we're going to start off by assuming that we have our sort of typical linear model, which is that y is equal to x times beta plus u, where u is a vector of errors. In this video, I'm going to show that the assumption, which is that the expectation of u given x being equal to 0, in other words the zero conditional mean of errors assumption, actually implies that the expected value of x primed times u is equal to 0. And furthermore, I'm also going to show that this implies that the covariance between one of the x's, call it xj, and the error vector u is also equal to 0. And just for clarity here, I'm saying that the index j runs from 1 through to p, so that there are, in this case, p independent variables in our model. Okay, so we're going to start off by working on this particular expression. So if we just write it down once again, we have that the expected value of x primed times u, which can then be rewritten using the law of iterated expectations as the expected value of x primed times u conditioned on x. Because remember that the law of iterated expectations will actually remove this last x when we take the unconditional expectation of this conditional term. But because we've conditioned on x, that allows us to separate out this term inside our inner expectation. Then what we can do is we can rewrite this as the expected value of, now what we're going to have is just x primed, because if we know x, then we know x primed definitely, so we don't need to condition on x anymore. And it's x primed times the expected value of u given x. So then if I close off that last expectation, we see that we're left with this latter term, which corresponds to our first assumption. And since this is equal to 0 in our assumption, it's equal to 0 here, and hence we have proved the first result, which is that the expected value of x primed times u is equal to 0. So we've proved this part. Now I'm going to work ahead and try and prove this sort of next step in our reasoning. In order to do that, let's first of all remind ourselves of what the matrix X looks like. The matrix X contains as our individual rows our observations for that particular individual. So we normally assume that we have a constant in our model, then we have x11, then x12, so the observation for individual 1 of variable 2 through to x1p, so the pth variable's observation for the first individual. And we have this for all n individuals in our sample, so we have 1, then xn1, and then xn2, through to, in this case, xnp. And we're sort of assuming here that all of the values in between are also filled out. A different way of writing this matrix X is to say that it is equal to a matrix where the individual columns are composed of row vectors which have been transposed. So when I write 1 primed here, I'm meaning a row vector of 1s which has been transposed to result in this column vector here. And then we have, for our first variable, x1 primed all the way through to xp primed. And the reason that I've chosen to represent our individual observations for a particular variable as a row vector transposed rather than just starting off with an ordinary column vector is just for notational ease later on when this will come in handy. Okay, I'm now going to shift to a new canvas so that I can prove the second part of that which I set out to. And now, since we've written x the way we have, we can write out an expression for x primed, which has as its individual components the row vectors which are transposed again, which just results in the original row vector. So we have a row vector of 1s, a row vector
corresponding to the independent variable 1 all the way through to the independent variable p. Then what we can do is we can multiply this vector through by, or this matrix through by u, and then we can take the expectation. So when we do that, we get the expected value of this times u, and remember u is here a column vector, which is equivalent now to being equal to, now we've got 1 as a row vector times u as a column vector, so this 1 here, just to be absolutely clear, has dimensions 1 by n. U has dimensions n by 1, meaning that when I multiply 1 by u, I get something which is 1 by 1 out. In other words, I'm just going to get a scalar. So this first component we're just going to write as the expected value of u, and u here is written in scalar form. Then as the second component, we're also going to get a scalar which is going to be equal to the expected value of x1 times u, which is itself going to be a scalar which is equal to, I'm actually just going to write it here as x1 times u in scalar form, which is equal to 0. And then if we go through each of these individual components, because of the fact that we know that this whole thing is equal to 0, each of these individual components has to be equal to 0 up until our expectation of xp times u, which is obviously also equal to 0. So our model here allows us to say that the expected value of xj times u is equal to 0, where here j runs from 1 through to p. And note here, actually to be technically correct, I should actually be writing xij times ui, but I'm just going to omit those two things for brevity here and for notational ease. So now I'm going to try and prove that this previous reasoning implies that the covariance of xj with u is equal to 0. So again, I'm going to use the scalar form rather than the vector form, just because I think it's a bit neater here. To start this, what we're going to do is we're going to start off by writing out an expression for the covariance of xj with u in terms of expectations. This is just equivalent to the expectation of xj minus the expected value of xj, all enclosed within parentheses, times u minus the expected value of u. So now we close that inside parentheses, and this is our expression for covariance. But remember, in deriving an expression for the expected value of x prime times u, we found that each of the individual components in this vector are also equal to 0, including the first component, which was just that the expected value of u was equal to 0. So that removes our last term from our covariance. So now if we expand out these parentheses, we get that this is equivalent to the expected value of xj times u minus the expectation of xj times u. We now know that because of this analysis up here, that we can actually get rid of this first term here because this is equal to 0. Then what we have to do is we have to then use our law of iterated expectations to be careful to make sure that we treat this last term correctly. This is equivalent to the expected value of xj times u conditional now on xj. And note that because of the fact that we're taking an unconditional expectation of a conditional expectation where we're conditioning on xj, this will just result in our unconditional expectation which we had before. But the benefit of conditioning on xj is that this first term here is now known. It's no longer stochastic because of the fact that we're conditioning on xj. And then what we're just left with is a term here which is the expected value of u given xj, which we've already reasoned is equal to 0. We actually prove this for the entire matrix of observations x rather than just an individual component xj, but if it's true for the whole matrix of observations, it's also true for an individual component. So this is equal to 0, and hence this second term disappears, and we've proved that the covariance between xj and u is equal to 0. I'm going to use each of these three forms almost interchangeably when I talk about econometrics, but note that in order to actually link these three things, you have to, in theory, go through the analysis which I've just done here, which runs in the direction that I've proved these three results.